Thank you. It's my privilege to introduce the next group. This is an iDesign group from environmental engineering, and they're going to be talking about their experiences at Valle Escondido. And it's Katie, Kristen, Hayden, and Dominic. Thank you.
Good morning. I do apologize. There was a discrepancy at like 8 this morning, which coffee was decaf and which was caffeinated. So if you're not feeling awake yet, it's my fault. Try the other batch. Yeah, as Jared mentioned, we were in Valle Escondido. I'm Hayden Henderson.
I'm Katie Blodgett. Some of which include a rainwater catchment system and various aspects of aqueduct development, from building a spring box to expanding our pipe network of the aqueduct, and also optimizing storage and treatment of the water in the system. And then at the end, we'll open the floor for questions. So a little bit about our community. The previous iDesign team went over the structure of the iDesign trip, so I won't go into that too much. Our specific community was Valle Escondido on the island of San Cristobal and Bocas del Toro, so same region as the previous team, but on this northwestern corner of Panama. But we were up in the islands up there, and then the expanded view, you can see Valle Escondido is on that island right off the coast, and so it was a gorgeous view. I mean, we got to be on the Caribbean island for a week, so we all had a really great time. And some facts about the community: that it is a group of indigenous Nobe Lupe people, which is the primary indigenous group in western Panama. They had about 300 people in this community, which is about 30 families, and their primary income was local agriculture, so yucca, bananas, cacao, those kind of things. And Katie Aaron was our Peace Corps volunteer. She was the 4th Peace Corps volunteer in this community, so they had a pretty long-standing presence, 7 years. So they were really open and welcoming to us when we came, and we all had a really great experience in this community. But it wasn't all fun and Caribbean sunshine. We did have to do a little bit of work while we were there, and so we created this fictional engineering company, Toto Deve Engineering, for the Nobe phrase for "it's all good," to evaluate these problems and find solutions. And the problems we were told going into this from our Peace Corps volunteer were that there were health problems in the community, mostly due to lack of clean water. And so our goal for our design was to diversify and enhance their water resource systems in order to consider their public health.
All right, so yeah, as Kristen mentioned, not all rainforests and roses. We did have quite a bit of work to do while we were there. Great experience culturally, but talk a little bit about the hard science that we got down to while we were there. So in the community, there's 5 wells that serve a couple families apiece. These wells are situated at the bottom of large cow pastures and down from homes that are practicing open defecation, just kind of a systemic practice. In a culture such as that, there is one main bathing area that's sort of a stream running through the community that everybody uses for bathing and washing themselves and clothes as well. And then there's 2 existing springs further up above some of the farms that feed the current aqueduct system. So just to get this out of the way, the aqueduct system is kind of one of those fancy engineering words for a pipe that's carrying water from a source to a tank, so don't get intimidated. So data collection, we also did some 3M feature films, as the previous iDesign group mentioned. The wells, not very surprising results, quite a bit of fecal coliform contamination and overall coliform contamination versus the spring water shown on the bottom here, featuring no E. coli and about 10 coliforms apiece, which that's a measure that's per milliliter of water within the system, and so a lot of those being naturally occurring and really no cause for concern. The contamination further down the line from the source to the tank and then the tank to the community, probably occurring from these broken and unburied pipes. They're exposed to children playing and animals in cow pastures and things like that, where they're frequently being fractured and allowing coliforms to enter the system. We did present these 3M feature films to the community, had sort of a water committee meeting. They don't have as much of a formal committee as some other communities, but were able to get them together and kind of offer this first visual representation for their poor water quality, and this was huge for them, I think, according to our Peace Corps volunteer. You know, it's tough without any formal education. Like we may have to really understand when someone tells you there's fecal coliforms in your water. That's on a microscopic level, that's something that's very hard to imagine. And so having this as a visual aid was incredibly beneficial in gaining their trust and respect, and allowing them to realize that we were there to help with this issue. We also had an idea going into the community that there may have been some issues from commercial farming with fertilizer use. That ended up not being the case, so that crossed something off of our list as far as concerns for water quality. The existing aqueduct system was essentially built by one person in the community, spanning a little over a mile, 6,000 feet of pipe with 200 feet of elevation change from the spring in the community, probably about a half-hour hike through the fields up to this source. And through all this data gathering, we kind of came together and developed some objectives in the community and with our Peace Corps volunteering, what we thought would be reasonable to accomplish. Those being some rainwater harvesting to supplement the aqueduct supply, and then also protecting the source. So the sources right now are essentially raw dug holes in the side of the hill. So we're getting a lot of sediment buildup and things such as that. We'll get into it a little bit later. And then also expanding the aqueduct. So there's 30 homes in the community. 17 of them are on the system right now, and they're wanting to get the other 13 homes, some of which are quite a bit further away from the center of the community.
So our first design objective was the rainwater catchment systems, and these systems are meant to help lessen the demand on the aqueduct system, as well as bring an alternative for clean drinking water to the communities. And these systems consist of an 85-gallon cement rainwater tank, which is shown above on the left. And then it's also going to be sitting on a wooden table with a first flush system. And this system is going to be put into the gutter before it reaches the tank. And that's to flush out any undesirable particles or bird droppings or anything that could come from the roof into the drinking water. And it's just to help keep sanitation. And we were able to collect monthly precipitation averages from a nearby region, Jung, and this is also in western Panama. And from this, we could determine that there's no dry seasons in this area of Panama. So it's going to be very feasible to use rainwater to help supplement the aqueduct system. And then from that, we collected local material estimates from our Peace Corps volunteer for the area. And per rainwater catchment system, it's going to be around $117 per home, which is a little over $3,500 for the community of 30 homes. And the Peace Corps is currently working on a grant to supplement this entire cost, but to keep the community members involved and keeping maintenance and invested in this project, they're going to pay a fee of $39, which will cover the raw materials and cement and wood for the tanks.
So as Hayden mentioned a little bit, a big part of developing this aqueduct is going to be protecting the source, and that's done using a spring box. The previous group talked a little bit about spring boxes. Our design is going to be a little bit different. We don't have a filter since there wasn't a lot of bacterial contamination in our spring sources, but mostly it's there to protect from sediment entering the box. So during research, we found there were two general designs for spring box design, and one with an open back or side and one with an open bottom. Since our spring sits on a steep hill, the open side would be very beneficial because all the uphill water would run into the spring box, but a lot of water is also fed from the bottom. So we integrated these two designs together to create our spring box, as you can see in the upper right-hand corner. Some other big important parts of the spring box are going to be the gravel and the large stones on the bottom that'll filter out sediment as it goes into the box. Clay around the box to prevent infiltration of contaminated surface runoff. And then a concrete apron to prevent erosion. Like I said, it sits on a steep hill and there's a lot of rain, so making sure that it doesn't wash out and slide down the hill will be really important. We estimated the size of the box just by estimating the size of the pool. It doesn't need to hold a large volume because we had storage tanks down the line, so just basically enough to cover the spring pool. And from those dimensions, we could calculate a volume of concrete. And this number is really important to us because it determines how much the spring box is going to cost to build. So as Katie mentioned, we got a cost breakdown for a rainwater tank using local material costs. And I used this to determine the cost of the spring box by basically figuring out how much more concrete we would need in order to create this spring box compared to a rainwater tank. And from the calculations, it's about 4.7 times more concrete, or about 5. So So we multiplied all those material numbers by about 5, rounded up, and was able to calculate a total cost of creating this concrete spring box to be about $261. This is just one spring box for the main spring. There's another spring that's currently on the aqueduct that's somewhat protected, and then a third spring that is being added to the aqueduct. So those are costs that we'll have to consider possibly down the line, is the addition of 2 more spring boxes. Protection at the beginning of the line is really important, but also protection at the end of the line is going to be important. A lot of the piping going into the houses was only 1/2-inch piping, so not very sturdy, and it was completely exposed to animals and children running around. So we wanted to give them just a simple design to be able to protect these pipes and reduce maintenance costs from damage in the future. So we decided on a material that's readily available, wood. A lot of the families around there already have access to that, and they could use 2x4s to create a box system around this pipe just to give it support and protection from going into their home.
And another big aspect of our project is to update the aqueduct. And so to do this, we surveyed the aqueduct down from the spring sources all the way down to the community. And up here is an elevation profile that we generated for just the source to the tank. And so at the right side, at the highest point, is the spring sources. And on the left side is the concrete tank. And it spans a total distance of about 1/2 mile with about an elevation change of 187 feet, an average slope of 7.2%. And this is the profile for the concrete collection tanks on the left down to the rest of the community. And it's about 0.6 miles with only an elevation change of 42 feet and a 2.6% slope. And using EPA Net, which is a pipe flow modeling software, we were able to map the general layout of the aqueduct system, which included the source, the tank, and the tank community line. And we compiled the survey data and input the elevations and pipelines in, and we made 2 models, the existing system and the theoretical system, in which we put all 30 homes on the aqueduct. And the purpose of modeling these systems was to optimize the pipe sizes in order to maximize flows down to the community, and as well as to determine if it was even feasible to add additional houses onto the water line. And this portion of the model shows the system from the spring sources down to the collection tank. At the top are the 2 sources, and then they both converge down to a single water line where they go down to the collection tank. And this is the existing model, so it's what it looks like in the community. And what happens is the water from the collection tank goes down the single water line, and it just branches off into the 17 homes. And like the previous model, water goes down the single water line, but this time there's 17 additional homes connected for a total of 30 houses on the water line.
Okay, so now we've protected the source of the water, right, and we've ensured the quality coming from that source. We've optimized it coming into the community, and now we really want to make sure that all of that is going to go to use. And so there's currently 3 1,250-gallon tanks seen on the right that are in the community, but are not currently used. So there was previously some complacency with the use of those, and they allowed some of the water to become stagnant, and they saw those just as a long-term storage as opposed to part of this system. And so integrating that with the other 500-gallon storage tank is part of our recommendation. They did have some complaints where this 500-gallon tank will sometimes be used up in a day if they've had periods of aqueduct breakage where they haven't had water for a few days and then everyone's catching up on laundry. They're using all their demand and emptying that tank and not relying on the over 4,000 gallons of storage that they have. And then another element of this is the treatment. We are going to recommend a chlorinator. So currently, the top of that concrete hatch is open, and some chlorine is poured in, maybe on a monthly basis, maybe on a bi-weekly basis, kind of depending on the motivation, with the community. So the treatment recommendations moves to this inline chlorinator. This was actually a program through the Ministry of Health in Panama a few years ago. Due to kind of lack of uptake with the sponsorship of the program, so it was a free program offered. $25 flat was the purchase price for the chlorinator, and then the tablets were provided by the Ministry of Health. That no longer exists, but the tablets are still available locally, and so we are recommending that this be placed in between the concrete tank and the larger storage tanks. So based on the types of pathogens that we're going to see in this area, contact time of about 93 minutes is going to be sufficient to chlorinately treat all of those pathogens, and that will assure this continued treatment of the water that's being there for storage and allow it to not become stagnant and degrade quality. This is also part of the ease of use aspect of a system like this. So I mentioned previously that one person from the community was walking up to the tanks and adding chlorine, Clorox occasionally. Right now there's one person managing all of this treatment and the whole aqueduct system. And so adding more of an automated system and setup like this ensures that as the water line responsibilities are passed down, that this is something that is continued to be used. So in summary, we presented feasible solutions for improving the quality via the spring box and the chlorinator that I just mentioned, and then also improving the quantity, so optimizing the storage that's there. And then also offering another supplement in the form of rainwater, which is currently in motion via our Peace Corps volunteer. So all said and done, we're looking at a little under $8,000 providing clean water to over 300 people. So very reasonable statistic for something such as that. Anybody have any questions?
What happens if your chlorinator breaks?
Similar to the rest of the aqueduct line, it's made out of PVC, and so it's somewhat readily
I was
available.
just hearing the word automated.
Oh, right. I guess I mean more so that the tablets are placed in the chlorinator, and it's a thoughtless process. So once those are in there, that's a monthly replacement, as opposed to a calculation based on the volume of water in the tank and how much chlorine would be needed and things like that. So those tablets plan for a treatment of 35 grams per milliliter, or 35 minutes per milliliter, which is the largest contact time for any of the pathogens that you would experience.
Thank you.
Any other questions?
Thanks for listening.